All right, morning everybody there, and we will get started momentarily looking at the previous homework and talking about some new stuff today. All right. So, last time, we've been talking about acids and bases. We've been talking about that kind of stuff. We've talked about the three different definitions of acids and bases. We've talked about calculating pH. We've talked about acid-base neutralizations, and we've talked about titrations. And so today we're going to kind of go through the homework, finish that up, and then look at one small new concept and do a little bit of review for the test that we're going to have on Wednesday. Okay, so let's see. Before we just jump right into the homework that is due today, any questions at all in general? Okay. I'm not seeing any questions. So let's just jump right into the previous time's homework. We've got a few things that we want to go through and just make sure we're understanding that stuff correctly. The front page may have been a bit of a challenge, but it shouldn't have been. The front page, we're looking at acid-base neutralization reactions here. And so let's just, last time we went through the first three, and then now we're just going to finish up these. All right, so make sure your homework is in, and let's go ahead and go over it now. All right, so we've got hydrobromic acid, HBr, and ammonia, and when they come together, so we can go ahead and write out that reaction, so we have a 1-to-1 ratio there. All right, and so of course we're thinking that HBr is going to be our acid. We've got an H here, and NH3, you know, it doesn't necessarily look like a base, but we've probably seen NH3 work before as a base, okay? And so NH3 is in fact a weak base. And so what can happen is the acid will take this H and it will donate it to the base, okay? And so it's going to simply look like this. And there's a couple ways we could write this, but let's just do HBr plus NH3. We could write this as Br minus plus NH4 plus, all right? And so here we have our acid and our base, and here we have our conjugate base and our conjugate acid. Or we could simply write this one product as ammonium bromide, right? We could write it as NH4Br. That would also be fine. Either way works, all right? And the concept is pretty much the same either way. All right, so next up, we've got one of this H3PO4 and two of the KOH. And so those numbers here are going to be important for how many we've got, especially because we see that this is a triprotic acid, H3PO4, and we have just a normal monoprotic base, if you will. And so what we're going to do is we're going to neutralize not one but two of those H's because we have 2 moles of our base, right? So we have 1-to-2 ratio, and so we're going to write our H3PO4 plus 2 KOH. We notice that the mole equivalence or the mole ratio here is going to tell us what these numbers here for balancing are, all right? So we don't even need to worry about it. We already know it's a 1-to-2 ratio, okay? And we are going to make some waters, right? So we have 2 hydrogens that are being removed here, and we have 2 hydroxides. That's going to make us 2 H2O. And in the end, that's going to leave us a 2 K pluses. And what's it going to leave? After you lose 2 H's here, you're left with HPO4 2 minus. Okay? So that's going to turn into HPO4 2 minus. And so I'm just going to write it as K2 HPO4. All right? Or you could write it as 2 separate things. You could write it as K plus, 2K plus, and plus HPO4 2 minus. That would work too. Okay? Just stop me if you guys have any questions as we go. All right, we have perchloric acid. We haven't really learned how to name that, but that's okay. All right, question. For products that have more than 3 elements in one compound like NHSO4, how do you know what order to put it in? Oh, good question. Typically, for things like that, and that's only going to be in the case when we have, let's say, a diprotic or triprotic acid. Typically, the cation is going to still be going first, and then the H, and then the anion. Okay? Because technically speaking, this is right. So this is a covalent compound, and if you have HPO4 2-, this is a polyatomic ion. All right. So the H isn't by itself. It's not actually an H plus here. This is part of a polyatomic ion. All right. So it's going to be the in this case, right. So the cation, and then the H to indicate that this is part of an acidic part of a polyatomic ion, and then the PO4. Okay? All right. So down here, we have perchloric acid, HClO4. We got 2 of them, and we've got this calcium hydroxide. Notice the calcium hydroxide has 2 hydroxides, and we have 2 moles of our acid here. So that's going to clearly neutralize each other completely. So we have 2 H's and 2 OH's. So that's going to be 2 HCl. Let me start over. 2 HClO4 plus CaOH2. That's going to get us 2 H2O. And then we're going to be left with calcium and perchlorate. So that's CaClO4 2. Okay, so that's that's FG. We have 1 H2SO4, and in this case, so yeah, this is interesting too. So we have 1 H2SO4, and we have 2 of these NH3s. So what's going to happen is, just like up in D here, where you have the H going from the acid to the NH3, we're going to have the same thing going on here. So you have the H's that are going to go from H2SO4 to NH3. This is your acid, this is your base. So it's going to be H2SO4 plus 2 NH3. And we're going to get, essentially, it's going to look like this. And once again, we have a couple different possibilities how we want to write this. But you're going to get 2 NH4 plus, and you're going to get an SO4 2 minus. Or you could simply write your product as NH4 2 SO4 and have one single product. Okay? Do we need to mark the charge of the product? You only need to mark the charge of the product if we have them as separate ions. I'm doing that just to kind of show you the 2 different products, so we can say, okay, this is the conjugate acid, this is conjugate base, but you don't have to. A perfectly fine way to write your answer is like this, and this would be your sole product, so one single product, and you don't need to write the charges when you have the full ionic compound written out. Okay? But if you split it into ions, then yes, you need to write the charges. So that's why I wrote charges here, but if you wrote it this way, you wouldn't have to. Okay. Last one, I had some questions about this, and I just asked people to think about it. The last one might be a little bit tricky, but think about what's going on. The last one is nice or confusing in that they both have sulfate in them. So this is sulfuric acid and this is sodium sulfate. And you think, okay, what in the world is going to happen? You don't really have a base. Well, actually, you do have a base. This would be your base. Okay? So just like, let me see, in this previous one in E, we didn't completely neutralize our phosphoric acid. We only neutralized 2 of the hydrogens, and we ended up with this K2HPO4, right? What this partially neutralized acid is kind of the goal, right? Is where it's going to be going to. So if you have a diprotic acid and a fully deprotonated conjugate base of that acid, what it can go to is the in-between product, okay? So one of these H's can go over here, and that's really interesting because when one H goes over here, this turns into HSO4 minus, and this turns into HSO4 minus. All right, so this is H2SO4, and this is SO4 2 minus, right? This one loses an H, and this one gains an H, and the product of both is exactly the same. So that's why it's kind of a little bit interesting there. So H2SO4 plus Na2SO4, and we can just write this as 2 because we're making 2 of them, right? We're making, so this is losing an H and making HSO4 minus, and this is gaining an H and making HSO4 minus. So we have 2 of them, and so it's going to be 2 Na plus HSO4 minus. And so this is the way you could write it. So as one single product, we could write it like this, or you could write it as 2 Na plus 2 HSO4 minus. But I just decided to write this one as a single product this time. Okay? So those are the neutralization reactions. All right? Some of them a little bit harder than others, but definitely expect to be able to do some kind of diprotic or triprotic acid or base on your test. So be prepared for that kind of thing. All right, but I'll make sure the numbers, just like this, where the numbers are all like 1 or 2 or maybe 3, I'll make sure the amounts here are all nice. Okay, so questions on those ones before we jump into the rest of the titration. All right, why SO4 attracts H is not, it's not really an attraction per se. It's just, you know, what can happen, okay? And so you have this, it's a level of acidity and basicity, okay? And so if we have, let's just look at something, and these are all interrelated products. You have H3PO4, right? You have H2PO4 minus, you have HPO4 2 minus, you have PO4 3 minus, okay? Of these, you could rank them all, right? This is going to be the most acidic, and this is going to be the most basic. And these things in between are all in between, okay? And in fact, this thing down here, this PO4 3 minus, is actually significantly basic, okay? That is a base. Right? This is an acid and this is a base. Well, why is this a base? It's a base because it's negatively charged. Just like hydroxide is negatively charged, this is negatively charged, and it will, H pluses will get attached to it. Okay? And I know we don't have enough time to really go down into any kind of detail with weak acids and strong and weak bases and all that kind of stuff and how they work. And you might get exposed to that later on if you take AP chemistry. But basically, if you would combine the most acidic with the most basic, they're just going to do an acid-base reaction, and you'll get something in between. Okay, so it's kind of just a stepwise process. If you add base to it, the first thing it's going to make is this. And then if you add more base to it, the second thing is going to make this. If you add more base to it, it's going to make this. Okay? And then if you have acid, it's going to go backwards. Right? Adding acid is always going to be going backwards. And so it's just neutralization. All right? And if you add strong acid or base, you can always get this thing to move one direction or the other. Right? So if we add strong base to this, we can get it to go all the way down here. If we add strong acid to this, we can get it to go all the way up here. Okay? And so it's all in equilibrium. It's all back and forth. You can always go one direction or the other. All right? So let's look at some more titration problems. And let's see. Oh, and there's even looks like we had a review problem on this one too. So a little bit of review, and hopefully we're not doing the same exact problems for. All right, question. Zoe has a question, but it's not going through. So he asked me to ask, all right, On the last problem you did the last live stream, it seemed that when the equation was balanced, the Cl disappeared. Really? You have to be specific. Do you mean, you don't mean this problem, do you? This titration problem? You're talking about a different one? I'm not sure. Let me look if I can find what you mean. I don't see anything. Let me see. Is this the problem you're talking about? Because this has a CO. Oh, okay. You're looking about, you're looking at this. Yeah, okay, this one. Okay. Great. So we have a base and we have an acid, and the acid, right. I didn't write down the Cl minus. Very good. So you do have a Cl minus. And it's partly because I had this unknown base here or something, and we're wondering what in the world that is. Okay, so maybe let's suppose this is just, well, we have a molar mass, so we can't actually, it can't actually be, let's say, sodium or potassium. It's going to be something bigger than that. But we have, let's just suppose whatever this is, for example, it might be sodium, then that would make sodium hydroxide as the product over here. Okay, so yeah, you do actually have a Cl minus. The Cl minus didn't just go away. It just was an ion that was floating around. Okay, so I suppose you should say, rather than base plus, this would be base Cl. Okay, and so that would be essentially your product there. Okay, all right. Hopefully that wasn't confusing. The Cl minus didn't just disappear into nowhere. It was floating around in solution, really doing nothing important, which is kind of why I ignored it. But yeah, it's there. And so it's going to make this ionic compound of whatever this base OH thing was, is going to now turn into base Cl. Okay? All right. So we're going to see a couple other of these types of problems, a couple titration ones from your homework. Let's go through those. All right, and we have number 3 here. We're going to titrate an unknown acid. You've got a sodium hydroxide solution, and we have a mass of the unknown acid. And you have a volume. All right, and so what we can do is, typically this mass, we're not going to use that until the end. So this mass is going to be used for calculating that that molar mass at the end, all right? And so what we're going to do is we're going to use this 21.3 and this 0.125. Those are going to be the numbers that we're going to use here at the beginning to calculate the moles of our sodium hydroxide, which is going to be equal to the moles of acid that we have, that unknown acid, all right? So I'm going to do it this way. I'm just going to say, all right, we have 21.3 milliliters, so that's going to be a 0.0213 liters, and multiplying it by our 0.125 moles per liter, right? Or you could just see, use your M equals N over V formula. And if we're solving for N, N is simply MV. Either way is going to work, exactly the same math. We're just going to multiply the two together. Remembering, of course, that this needs to be converted to liters so that the liters over liters cancel out. Otherwise, you're going to get something that's going to be 1,000 times off. So 0.0213 times 0.125 is going to get me the number of moles. Now, it looks kind of small, which is understandable. 0.00266 moles of sodium hydroxide. Now, we have, let's assume it's monoprotic. What does monoprotic mean? Monoprotic means, so this is moles of sodium hydroxide. Monoprotic would mean that we have this many moles of our unknown acid, okay? Now, if it's diprotic, then we're going to have half of that. All right, so that this is monoprotic. If it's triprotic, it's going to be 1/3 of that, okay? And we can just go ahead, let me just store this in my calculator, and I can go ahead and divide by 3 and get this really, really small number. So 1/3 of that is 0.0008875. That would be moles of acid that I had if it was triprotic. Okay? So I'm first going to look at it if it's monoprotic, if it has that many, and I stored that value in my calculator as X. So the molar mass of this is going to be the mass, so molar mass is going to equal the mass of that unknown divided by the moles of the unknown. So that's 1.345 grams divided by 0.00266 moles. So it's going to be X divided by, no, it's going to be 1.345 divided by X. And that's going to get me a really, really, really big number, which is a little bit crazy, actually. 505 grams per mole. All right. Now, we have, let me see, what's the molar mass if it's triprotic? Now, if it's triprotic, then it's going to be even bigger than that, right? Because it's going to be 1/3 the number of moles, and so it's going to be essentially 3 times the molar mass. So you could literally just go times 3 here, and obviously these numbers are fairly unrealistic unless, let's say, maybe these are biomolecules or something like that. Then it's perfectly reasonable to have large numbers. But this is going to be our monoprotic number. And this is 1, 5, and we have 3 significant figures. So 1520 grams per mole if it's triprotic. All right, so questions on that one. Number 3. Some fairly large numbers there for our molar masses. All right. And then same exact procedure for number 4, except there's kind of a different question about it. So rather than we're calculating the molar mass, it's getting us to calculate the concentration. But the way we start this is going to be the same. Okay? So jumping down to number 4, suppose we titrate a concentration, an unknown concentration of 50 milliliters of HCl. So once again, this number that's unknown, whatever that number is, whether it's a mass of the unknown or a volume of the unknown, that we're going to wait till the end to use. We're always going to start with known amounts. So we have a known molarity of sodium hydroxide and a known volume of sodium hydroxide. So we're going to use those together. So it's going to be 0.0768 liters of our sodium hydroxide and multiplied by 0.275 moles per liter, and that should get us the number of moles that we have there. 0.0768 times 0.275 will get us 0.0211 moles of our sodium hydroxide. Okay? And we know what our acid is, right? We know it's HCl, so we know for certain that that's a monoprotic acid because we know the formula. And that means that if we have 0.0211 moles of sodium hydroxide, we also have 0.0211 moles of HCl, because that's what it means when you titrate it and you come to the equivalence point, those two amounts are going to be the same. Last of all, once we have moles, this is fairly straightforward. We know that this is going to be our value for N. We have 50 milliliters of HCl, which is 0.0500 liters of HCl. That's going to be our volume. And so our concentration or molarity of that is N over V. So it's going to be our 0.0211 moles over 0.05 liters. And I just use the number I have in my calculator to avoid any kind of rounding error. So take that number divided by 0.05, and it gets me a concentration of 0.422, 3 significant figures, moles per liter. Okay, so that's going to be my answer for number 4. And I'm just going to pause there as we do that's our last titration problem. Any questions at all? You will have one titration problem on the test, which will look like one of these. Not sure which one, but it'll look like one of these. Okay? All right. Any questions at all? Number 5 is a bit of a review. So we're doing a significant amount of review here of figuring out, okay, what's an acid, what's a base, all that kind of stuff. Bronsted-Lowry theory is going to be the most important one for us for acids and bases. You'll see some Arrhenius acids and bases on the test, and then maybe one little tiny question on Lewis acids and bases. But Bronsted-Lowry acid bases is definitely going to be the most important one on the test. So we're just going to be looking at these and say, okay, which one's losing an H, which one's gaining an H. So we can go through them. We look at, okay, NH3 is going to NH4 plus, so it's gaining an H, which means this one must be our base, and this is going to be our conjugate acid, which means the other thing must be the acid. It's going to go from HNO2 to NO2 minus, so clearly it's lost an H, so this is your acid, and this is your conjugate base. Okay? Now we have NH3. NH3 here is going to NH2 minus, which means that the NH3 is actually the thing that's lost the H. And this is a nice one because right here NH3 is acting as a base, here NH3 is acting as an acid. Typically speaking, NH3 acts as a base most of the time, but it could certainly act as an acid if it's reacting with a very strong base. So NH3 going to NH2 minus, this is going to be your conjugate base, all right? And this is your base, and this is your conjugate acid. You don't typically see OH minus as a conjugate acid, but in this case, because your base is oxide, that's why we're having hydroxide as a conjugate acid, all right? Here we have perchloric acid reacting with water, just a nice, simple kind of ionization reaction and just dissolving acid in water. So very, very straightforward for this one. So this is your acid because going from here, turning it into ClO4 minus, all it's doing is losing an H plus. So this is your acid, this is your conjugate base, making water in this case our base, right? Water is gaining an H, going from H2O to H3O plus, so it's gaining an H. So this is our conjugate acid. Last of all, we have, look at this. We have 2 different acids. If you're Arrhenius, you'd be looking at 2 different acids, right? This is perchloric acid, this is hydrobromic acid. But it looks like this HClO4 is turning into H2ClO4 plus. It's actually gaining an H, which means our strong acid is actually now acting as a base. And this is our conjugate acid. And hydrobromic acid, a very, very strong acid. And this is our conjugate base. Okay? So that's number 5. I like all those. Those are good ones. I think, I know on the first time I gave you guys this, I gave you some questions that had, I think something like lithium hydride. I'm going to avoid that on the test. So that was a little confusing. We're not going to see any hydrides on the test. These are certainly good questions that you might see on the test. And so make sure you focus on this rather than looking at the really weird ones that were on the first homework. So this is all your answers for this homework. Any questions before we jump into new stuff? Now, if you haven't seen it already, I did post it a little bit late, but I've already posted the homework that's due tomorrow. And the homework is kind of half new stuff, half review, so that'll help you guys out on the test. Expect a fairly short test because we've only done a few things this particular unit. We haven't covered everything for acids and bases that I'd like to, but you know, with the whole coronavirus stuff and with me out having a baby, we just didn't get to cover it, and that's okay. I'd rather just finish up with acids and bases and start something new after spring break. So we're going to have our test on Wednesday. It's going to be a short test. Your previous test has been graded, and the grades are all up in Google Classroom. I haven't put them over in to OneDrive yet. I need to, not OneDrive, I mean into Facts yet. So I'd like to do that probably today. All right. Now, this is not a question. I see a statement. I am confused with neutralization. That's not a question. I need a question. Questions I can answer. Confusion, I cannot answer that. So if you want me to explain something, I can try. Leo, what would you like me to actually answer? Is there anything you'd like me to answer about neutralization? All right. And I know you had a question earlier about the whole thing with what was going on when you were, why did this attract an H, right? So just keep in mind this is always a continuum of what's going on, all right? And when you neutralize something, think of acids or bases as fairly unstable things. It's not exactly the way to think about them, but think of them as fairly high energy things, okay? And so when you take an acid and base, they come together, you're going to make it something that's going to be neutral. All right, so here's a question. How can we determine the products will be like in question H? So like in question H, you have to just think of what can they possibly do, right? Well, what else can you do for problem H? All of these, as you know, I'm going to tell you it's an acid-base neutralization reaction. What does that mean? That means that an H is going from one thing to another thing, okay? And so, in all honesty, there's not a whole lot of possibilities. In fact, there's really only one possibility here. There's nothing else that can go on, okay? If there's a reaction, okay? So we can think of three different possibilities. So first of all, the sodium in your acid-base reactions, those things are always going to do nothing, okay? And so the first thing, if you want to simplify this a little bit, you could think of this as a reaction between H2SO4 plus SO4 2-. That's the reaction, right? Forget about the Na. The Na is doing nothing, and those cations are going to be doing nothing. When you have sodium, lithium, potassium, they're going to be doing nothing. So there's really three things that could, there's actually literally only two things that this could possibly do, right? If it's an acid-base thing. Either it's going to do nothing, or you're going to have an H go from here, okay? Because if we have two H's go from here to here, then that's nothing, right? So we always look at these acid-base reactions as happening in kind of a stepwise fashion, okay? First, we're going to lose one of them, all right? So this is going to act as an acid. It's going to lose one H+. It's going to turn into HSO4-. You find the thing that can lose H+, and then you take it away, all right? And then the other thing must be able to be something that's going to gain an H+, okay? So when that gains an H+, what will it turn into? It's going to turn it into HSO4-. Now, you could possibly have this one lose another H+, and this one gain another H+, and that can happen sometimes. But if you did that, nothing would happen. Let's look at something a little bit more interesting, a different problem, okay? Let's suppose you have H3PO4, and we're going to react it with PO4 3-. They will definitely react, okay? This is an acid, not a strong acid, but almost strong acid, and this is going to be a strong base, so they're definitely going to react, right? This one has 3 hydrogens, this one has none, okay? Now, it really, really matters how much you have. Why? Because if we do, let's say we just remove one H, right? So I'm going to write it this way, minus H+, is going to turn into what? It's going to turn into H2PO4-. And let's suppose in the process, this is going to gain an H+. That turns this into HPO4 2 minus, okay? So that's interesting. If this were to lose another H plus, that would turn that into what? That would turn that into HPO4 2 minus. And if this were to gain an H plus, that would turn this one into H2PO4 minus. Notice, interestingly enough, if you stop, let's do it this way. Whether we stop here or stop here, the result is going to be the same. Why is that? Because we have H2PO4, H2PO4 minus, H2PO4 minus, we have HPO4 2 minus, HPO4 2 minus. So whether we stop here or stop here, the result is the same. And so what's going to happen in this case, let's suppose so we have just one of these and one of these. What they're going to turn into is this. We're going to turn into H2PO4 minus and HPO4 2 minus, and we're going to stop, okay? And you're going to have some other, that's going to be your reaction. And so if we were to write this out, it would look like this. It would be let's see if this is on the screen. Yep. It would be H3PO4 plus PO4 3 minus. And this might be sodium phosphate or whatever. And it's going to make H2PO4 minus plus HPO4 2 minus, okay? And this is probably perhaps the most challenging thing that you might possibly see. So you have a lot of crazy stuff going on, right? You're asking about the most challenging problem that I gave you guys, and this one's even a little bit harder, but we can see that there's no other possibilities, right? When you look at these acid-base things and you try to think, oh, why does this happen or why does that happen? There's literally nothing else that can happen. And when you do this reaction, you're trying to make it as stable as possible. And so this is the most acidic, this is the most basic, and so you want to go towards the middle if possible. You want to make something as neutral as possible. That's why it's called an acid-base neutralization. Acids and bases are reactive chemicals and they try to neutralize each other. So if we go back to a simple acid-base neutralization reaction, we see exactly the same thing, right? HCl plus NaOH. This is a strong acid. This is a strong base. They are both highly reactive and they want to make something more neutral. So what are they going to make? The H is going to go to the OH minus to make water. That's neutral. And the sodium and chloride are going to be left together, NaCl. That's neutral, okay? And so as much as possible, we're going to take these reactive acids and bases and neutralize them to make water and then something more neutral. And so although this one, in this case, you don't make any water, we do make things more neutral, right? More neutral. And that's kind of the goal in this. But remember, if you get stuck, just think what can possibly happen? We have to move an H around, and there's only so many different things that can happen. Now, unfortunately, I didn't realize that I kind of just really got lost track of time there, which, yeah. So I only have a couple minutes left to talk about the new stuff. Fortunately, the new stuff is fairly simple, but I'm going to take 5 minutes to go through this, okay? And so we'll once again end class a little tiny bit late. So 5 minutes to go through buffers. Now we're not going to get to complex buffer stuff, but I just want to simply tell you guys what these things are, okay? So new stuff here. I posted this up on Google Classroom, so you guys should have a copy. What is a buffer? A buffer is going to be something that's going to resist change in pH. And it'd be really cool to do a lab on this, but unfortunately we don't have the ability to do labs right now. And how is a buffer made? A buffer is going to be a weak acid plus its conjugate base, or, and this is really the same thing, or it could be a weak base plus its own conjugate acid. All right? And so that's what a buffer is. A buffer is going to be something that's going to resist change in pH, and you need to have a weak acid or a weak base and its conjugate base or conjugate acid. So that's kind of the way a buffer is made. And I actually want to skip down to number 4 here because it's kind of directly related to this. And so let's talk about, so acetic acid. So that's the same acid that is in vinegar. Acetic acid is a weak acid. How could you make a buffer? And very simply, the most straightforward way, there's literally 2 ways, but you only need to maybe really know one, but there's 2 ways. We could add its conjugate base. What's this conjugate base? So if we take away the H from that, it turns into C2H3O2 minus. So we're going to add C2H3O2 minus. And specifically, one way to do that would be to add sodium acetate. Now, it would be ideal to have equal amounts of acetic acid and sodium acetate, but it doesn't have to be. It doesn't have to be equal amounts. All right? It can be just some of this and some of that, and now it's already a buffer. All right? Or one other way is to partially neutralize it. And when we partially neutralize it, what we're going to do is you're going to add a small amount of, let's say, sodium hydroxide. Okay? So what would that look like? That would look like 1 mole of HC2H3O2 plus, let's say, 0.5 moles of NaOH. Well, why is that going to make a buffer? Because when that happens, half of this gets neutralized and turns into the C2H3O2 minus. So half of this turns into its conjugate base. When you partially neutralize something, not fully neutralize something, you're going to turn the acid into its conjugate base. Now, question, how can we determine the, oh wait, yeah, that was an old question. All right. Now, if you're wondering, how do you know whether something's a weak acid or a strong acid? Don't worry, I will tell you. I'll say this is a weak acid or this is a strong acid. Okay? So don't worry about that. All right? That would be beyond the scope of what we have time to do. All right? So acetic acid, I will tell you, that's a weak acid. All right? So you can either add the conjugate base or you can partially neutralize it. Either way is going to make exactly the same thing, a buffer. Okay? Now, a weak acid and a strong acid, though the strong acid is going to make, it's going to completely ionize, so 100% ionize, and the weak acid is going to only partially ionize. Okay? And that partially is probably going to be, let's say, less than 50%. Okay, so it's only going to ionize to a small amount. So when you have a weak acid or a weak base, it's not going to turn into, so if you have, let's say, 1 mole per liter weak acid, it's not going to be 1 mole per liter H+. It's going to be significantly less than that. So that's what the difference between a weak acid and a strong acid is. All right? Now, couple more things here. So this is going through conjugate acids and conjugate bases and looking at, okay, we don't necessarily even need to have a chemical reaction to find out, well, what's the conjugate acid or what's the conjugate base of something. And so we can simply say, okay, when you have H2O, the conjugate acid, and let's just make a little table here. The conjugate acid is simply going to add an H. So this is going to be H3O+, right? The conjugate acid of NH3 is going to be NH4+. We're just adding H+ to that to make the conjugate acid. To make the conjugate base, we're going to remove an H+. So H2O minus H+ is going to be OH-. NH3 minus an H+ is going to be NH2-. So taking away an H+ turns it into the conjugate base. Adding an H+ turns it into the conjugate acid. All right. Last of all, before we end here, is number 6. how can we tell whether something is a buffer or not? So I'm not even going to write this down. You guys can write these all down yourselves. I'm going to talk through these and you guys can think through them yourself later. So A, we have HCl. Well, I tell you, HCl is a strong acid. So, and you have sodium chloride, which is just salt, right? So that can't possibly be a buffer because it's a strong acid, right? When we come down here, if HF, well, it says HF is a weak acid. So if HF is a weak acid, we have F minus, which is this conjugate base, that's going to be a buffer, right? A weak acid and its conjugate base. A weak acid and its conjugate base, right? And then if we have down here, we have HF and NaOH, right? So this is a weak acid and we are neutralizing it, but we have 0.5 moles and 0.5 moles, which means you are completely neutralizing it. And if you completely neutralize it, it's not a buffer. You have to partially neutralize it. So what's that going to look like? If you have 0.5 moles of HF and you have 0.25 moles of NaOH, that's going to partially neutralize it, and that'll be a buffer. All right, so we're going to talk about this more later. I'm just going to sign out here. Have a great rest of your day. Peace.